Meet Pogo. Pogo has a great photograph, and he really wants to share a memory with his computer. When we look at this, we immediately see a golden retriever puppy running through the grass. We recognize the furry face and the floppy ears. To a machine, this picture is a massive grid of tiny solid-colored squares, called pixels. Grouping those tiny squares together to recognize a puppy is entirely natural for us, but a computer requires a completely different method to make sense of all that raw data. The old way involved breaking the image apart. The computer read the grid row by row, stretching it into one endlessly long line. This ruins the physical layout. Two side-by-side brown pixels in the puppy's eye are now pushed hundreds of blocks apart. In a picture, neighbors matter. The specific way colors sit next to each other is what creates a curve, a shadow, or a shape. If you scramble the neighborhood, the shapes disappear entirely. To actually understand a photograph, a computer has to leave the image exactly as it is, a two-dimensional grid, and analyze it without moving the pieces. The solution is to look at the unbroken picture through a tiny square viewport. Think of it like a little magic bamboo frame. The computer places this frame at the top corner. It reads the pixels inside, then slides over one step. It repeats this motion across the picture. While sliding, it calculates the colors inside to check for one pattern, like a sharp edge or curve. When the colors inside the frame perfectly line up with that pattern, say the curved shape of the puppy's ear, the computer registers a hit. It takes note that it found that exact shape right at that specific spot. By scanning small chunks one at a time, the computer acts as a pattern finder. Instead of being overwhelmed by the whole picture, it builds an understanding of the image piece by piece. This sliding method brings up a new challenge. What happens if our puppy isn't standing perfectly in the middle of the photograph? The frames sweep systematically across every inch of the picture, detecting the curve of the ear, even if the puppy is on the far right. If the puppy bounds over to the far left side of the grass, the sliding frame sweeps across and finds the exact same curve there. The computer learns that a puppy's ear is a puppy's ear, regardless of where it happens to appear on the screen. A single frame looking for one curve isn't enough to recognize an entire animal. The computer uses dozens of these sliding frames at the same time, searching for different features, looking for straight lines, detecting dark shadows, and identifying complex textures. This flowchart illustrates how discoveries are grouped. The first layer finds simple lines, passing them to a second layer that combines them into shapes, like an eye. Finally, detecting these parts gathered together, it confidently names the object a dog. A convolutional neural network is a series of these sliding frames stacked on top of each other, working together to turn dots of color into recognizable objects, like puppies. There is one last hurdle. How does the computer recognize the puppy when the camera is far away, capturing the whole yard, versus when the camera takes a massive, zoomed-in close-up? If the computer's sliding frame is a fixed size, it will easily miss a giant nose because it only knows how to look for a small one. Objects change size depending on the camera. The computer needs a way to step back and look at the whole picture, so that massive shapes match its memory of tiny ones. To solve this, the computer uses a technique called pooling. You can think of pooling as the computer intentionally squinting or taking a big step backward from the photo. It takes a detailed block of pixels, say a 4x4 square, and mathematically averages them out to create just a single new pixel. This reduces the overall resolution, physically shrinking the picture grid. By shrinking the picture itself, the massive shapes get smaller. Now, those giant ears and noses fit perfectly inside the computer's original small sliding frames. By combining tiny sliding scanners to find patterns and then stepping back to simplify the view, a computer can move past raw numbers to finally see the world with the same understanding that we do.